It's been so long since I flew that I don't even remember what the transfer for rockets.
I remember for Cray for years.
Does Cray work good as a game server?
No, not really. Not a whole lot of games on it. I've never seen Doom on a Cray.
Or do is slightly swapping.
Es un tremendo beneficio porque por lo menos no me quitan el 25% de lo que yo gano. Si yo pudiera gastar el dinero por algún tipo de gasto, para efectos del gobierno yo estaría ganando eso, pero igual estoy recibiendo, pero me la tengo que poner en algo.
Taking a little bit here?
Yeah.
There we are. Lots of swap outs going on right now, yeah.
La gente que tiene
ESWOT?
Block swapped out, yeah.
Major.
Okay, so we need to talk about CPU. We're getting away from I/O, but we're going to come back to I/O. So a couple of key parameters that you should be familiar with already, nproc and maxup. nproc controls the total number of processes on the system. We cannot have PS report anything more than nproc. And remember, only root can take the last entry in the process table. I do not advise maxup to equal nproc. I hit that on one machine, I logged into the machine, it was a machine here and I was doing some development work and I got a recursive script that fired off and it just plugged the process table with all these processes and then I didn't have any more slots left to even SU to root to be able to do anything. So nproc is the maximum number system-wide, maxup is per user, and also remember we hit job limits. With job limits you can mark another parameter there. There's a JLimit maxproc environment or system parameter. So, process execution. Hopefully an executing process is doing useful work. Yesterday when I talked about unuseful work, we talked about TLB misses, cache misses, and barrier synchronization problems. So those have to be fixed other ways. Now, IRIX, like Unix and Linux and the newer operating Windows systems, is what's called a preemptive time-slicing operating system. This makes it look like each program gets the whole machine, but the operating system gets a clock interrupt and periodically switches which program actually gets the CPU. Now if you were on older Windows 3.1, you actually had to hit a key to switch from one application to another. It did not allow what we would call multitasking. So time slices is how we limit the time a process can run before it gets kicked off the CPU and some other process can come in. And what do we call it when a process gets kicked off a CPU and another process gets it? A context switch. So context switches are counting the number of times I'm swapping a program in and out of CPUs. Okay? Now I'm going to break away from the slide for a minute and go over here. When I'm running along, the first thing that can kick me out of the kernel is system calls. So I've always said, if you don't need system calls, stay out of the kernel. If I'm going into the kernel 100,000 times a second to get uname, that gives the kernel a better opportunity of taking the CPU away from me. So every time I get a system call, I go into the kernel. This is called a voluntary context switch if I lose the CPU. Remember on SS usage, we were able to get that statistic. Number of times that I lost the CPU and somebody else got it because of a system call. So if I'm doing 100,000 calls per second, that gives the kernel 100,000 times opportunity to give the CPU to somebody else. Okay. As I'm running along, the next one that occurs is called a minor clock tick. This is every 10 milliseconds. Okay. So every 10 milliseconds, I will look at the processes and pick the top of the run queue. The run queue is ordered by priority, if you want to call it that. And we're going to talk about that in a couple of slides. So when I go to the run queue, the thing at the top of the run queue is the one that I should run next. The next opportunity that comes along is called slice size. And that's what we have right here. The purpose of slice size is to slow down my context switching. So slice size is a system parameter, but with NPRI, I can change different CPUs to have different time slices. Or I should say different processes can have different time slices. So the purpose of a slice size is to slow down my context switching. Now on your workstation is typically 2, which would be times the minor clock rate, which is 10 milliseconds. So on a workstation, it's actually a 20 millisecond interval. Let's just call it workstation. And on the origins, it's 10 times the clock rate, which comes out to 100 milliseconds. I'll just say for the 3K. So the slice size is simply a way of slowing things down. I'm going to get rid of this. But slice size is multiplied times your tick. How many ticks do I get? 2 ticks or 10 ticks? The next opportunity to kick a process out of the CPU is my major clock rate. And this is once a second. Let me put it up here. By the way, these minor clock ticks were called involuntary context switches. And it's the minor clock ticks that allow the operating system a chance to check to see whether I should schedule somebody else. But during the minor clock tick, there is no priority decision. We do not compute priorities or anything like that. We simply pick whatever's at the top of the queue. One other thing that I was going to say is during this minor clock tick, we also do accounting. And also check mem. Check for free mem. We'll just say check memory space. Do I have enough memory available? So every minor clock tick, we also do accounting statistics, SAR, and per process accounting records are checked. And also say, do we have any memory available? If we're running out of memory, we may actually wake up VHAND to say, resolve my memory shortage problem. Now when I get to the major clock tick, I will reorder the run queue. Okay, so that's where I do my priority decision. So once a second, I determine my new priorities. Now, unique to IRIX 6.5 are 2 new opportunities for scheduling. These are unique to Miser. Now that's where we're going the rest of the day, is to get our code 2s running under Miser. With Miser, it's like a restaurant reservation system, and I call up the restaurant and say, I want a table from 7 o'clock to 8 o'clock tonight, and there's going to be 10 of us there. And then Miser goes to a reservation book and says, yes, you're available from 7 o'clock to 8 o'clock, and yes, I can see 10 people at the table. If you called the restaurant, they have a book with a grid in it. The smallest granularity of the reservation book would be like 15 minutes. So I call the restaurant and they say I can come in at 7, 7:15, 7:30, 7:45. That's the size of the grid of the reservation book. The concept of that would be something called a quanta. So a quanta is the smallest time that I can reserve my CPU through Miser. And by default, that is 20 seconds. I'm sorry, yeah, 20 seconds. I usually up it to 30 seconds, but the default is every 20 seconds. The point being here, if I've got a process that's going to run for a month, why decide every 10 milliseconds whether I want to run it or not? Let's just lock it down and leave it alone. And the purpose of Miser is to reduce system cache thrash and also to protect the program from memory, from swapping. So when I call up the restaurant, they say 15 minutes, 7, 7:15, 7:13. That's the same thing as a quanta. The next thing that Miser has is called a segment. And a segment would be all the quantas within a given reservation period. So if I call the restaurant and I say, I want a table from 10 o'clock to 11 o'clock, and then they say, I'm sorry, we're open from 10 a.m. to 10 p.m., that would be considered a segment. So a segment would be your normal time span that you would offer services to. A job cannot span a segment. So the restaurant, I call and say, I want a table from 9:30 to 10:30, and they say, but we close at 10 o'clock. They would then move that reservation into the next segment, because I can't span a segment. Now, originally Miser was considering segments to be 1 week long. So Miser was intended for the jobs that are 8 hours, 24 hours, or 7 days, typically. We then had one site setting up Miser that stuck a couple extra zeros there, and basically 2 days later, Miser was still building a reservation chart for 10 years worth of CPU time. So we put a limit on segments, and it's like 2 months. So if you have programs that run longer than 2 months, they don't belong in Miser. Now most people are doing 1 week segments. And some of these people, I've got samples of a 1 week segment schedule that has prime, non-prime broken into it. So we count the number of quantas going from midnight to 8 a.m., and then the number of quantas from 8 a.m. to 5 p.m., and then from 5 p.m. to 8 a.m. the next morning. So we can set up a prime, non-prime segment structure such that during prime we don't use Miser, and during non-prime we do. So just think of Miser as that reservation book that is keeping track of everything in. The quanta would be the size of the grid, and the segment would be how many quantas can I put together in a given interval. So I go to Perkins or McDonald's, they're open 24 hours a day, not a problem. But other restaurants may close at 10 p.m. and I can't schedule stuff past 10 p.m. to the next morning. Okay. And again, the whole purpose of Miser is to stop the CPU scheduler from interfering with these programs, to just leave them alone and let them run. And a job cannot span a segment. If it hits the end of a segment, it will get killed. But Miser guarantees your CPU and your memory resources. Now Miser isn't that popular out there. There are people doing other things. It's not the only way to do things. There's also something called CPU sets. So NQE is using Miser, but PBS and LSF are using CPU sets. CPU sets do not have a reservation concept. A CPU set, I just lock it down, but I don't say how long I'm going to use it or anything. It's not a reservation concept. So CPU set is a way to give private dedicated affinity, but it doesn't say how long. So I can't get predictability of when the next available reservation time is going to be available. So we've got Miser or we've got CPU sets. And NQE is using Miser, whereas PBS and LSF are using CPU sets. So I need to show you both. Okay. So this is what we mean by a preemptive time slice operating system. It's just that within IRIX we've added 2 more scheduling intervals, a 20-second quanta and typically a 1 week segment, the maximum being a 2 month segment. So every time we go into those 6 different opportunities, the kernel says, should I run somebody? Anyway, going back to the workbook, also we had process limits. There was R limit, CPU max, and CPU current. We've talked about that. You log in, you get current, and the limit command ups you to max. And we now have per job limits as well. So when a program is running, or in the system, it's in various states. The most common, hopefully, state is running, connected to a CPU, executing. That's showing up as user time or system time. The second stage is where I blocked on a lock, and the WCHAN field told me what lock I'm sleeping on. And again, blocked or sleeping are essentially the same thing. The process voluntarily yielded the CPU. In other words, it made a system call, and every time you do a system call, there's an implied yield. Now, what system call actually meant yield? What was the system call whose whole purpose in life is to yield it?
Sleep.
Sleep is one way, but with sleep, I don't get it back right away. With sleep, I have to wait until the time event occurs. SGI nap. In the Cray world, it was reschedule my CPU. So I could have made the whole purpose of an SGI nap is to say, kernel, I can't use my CPU anymore, give it to somebody else. That's the purpose of an SGI nap. In Linux, it's called nanosleep. The third state means I'm switched out, and a couple of you asked about this. With the casync name D, there was no lock name there, it was a dash, but there was no CPU number in the CPU column. So the only difference between running and switched out is that there is a CPU number in the CPU column, and switched out there isn't. This switched out is going to be counted as CPU wait time. So a process executes until the end of some sort of time slice, or it's preempted by a higher priority process. Again, a transition from one process to another is called a context switch. When we do a context switch, everything about the prior program is dumped into memory, and then the new program is loaded into the registers. So the operating system saves off all the register information that's in the chip. Now I should warn you about this and talk about it right now. SAR-W, I guess I got one right here, has 2 columns describing my context switches. The first one is to user processes. The second one is to kernel threads. Now right now in this sample, my user context switches were 400 or 500, but my kernel context switches were actually higher, almost twice as high. Now I happen to know what that was in this case because we had swapping going on, and we were context switching to VHAND more than likely during this interval. Let's see if we've got anything going on right now again. To try to get a normal context switch. Right now we've got both rather high, 2,000 per process and 2,000 to the kernel as well. Up top, we've got all these code 2s running. And now is probably as good a time as any to describe how to look at context switches. Does anybody remember the command that will let you see all the context switches? Begins with P, AR, -R. The -R option is going to save off all my context switch information. So with that SAR-W option I had, I can actually go in, don't see it anymore, I can go in and actually see what those context switches are. So I got 3,000 to users, almost 3,000 to kernel. So I'm going to run a par-R, I'm going to use a -big O and put it into a X file. -T, I'm going to go 15 seconds. And again, I want to be looking at a typical interval. So since I do have code 2s running right now, and that is the purpose of my machine, I feel it's an appropriate interval to be looking at things. So par-s gave me system calls. Par-k gave me what was coming out of the back end of buffer cache. And par-r gives me my context switches. Now IRIX view can view this, but I never did load IRIX view, and I don't think I'll get a chance to use it. But IRIX view is a GUI to look at this context switching. So, to take a look at this trace now, I'm going to do a par dash, and for whatever reason they chose to use Q instead of big R. They chose big Q to view that trace. So I'm just going to take a look at that X file, and I should probably just put it into a file. And this was the non-verbose one, by the way. This is the CT file. So now if I look at CT file, in here now, for each CPU, so during that 15 seconds, I had an average of 2466 context switches per second. So I collected with par-r 15 seconds of data. And then for each CPU, it gives me a summary saying, idle was 0, so we have a busy system. Total milliseconds running, we were 100% saturated during that 15 seconds. And during that 15 seconds, I dispatched or started to run 1,129 processes. 1,121 of them came from my local run queue. Every CPU has its own run queue. Remember, that was for scaling. Older crays, I'd often see the run queue lock as the biggest thing. I got 32 CPU cray and the run queue lock was there. So each CPU has its own run queue with its own lock. That way when I look for work, I look at my own run queue first and there's no lock on it from another CPU. So 1,121 times I pulled the process off of my run queue. 8 times I had to go somewhere else. Maybe I went idle, there was nothing on my run queue, and I went to a global queue to look for work. So the rule is I look for work on my CPU first, then I look for work on my neighbor CPUs. It is a pull mechanism. So if I go idle and another CPU has a process running and a process waiting to run, I will take the waiting to run process and pull it into my CPU. It's a pull mechanism. And that's what causes thrashing in the system, where a process starts bouncing around in the system. And par-r is the only way to see the thrashing from CPU to CPU. So par-r will actually show me getting disconnected from one CPU and getting connected to a different CPU. So, 64 times I ran the same process, which was 5.7 of the interval. And 850 times, or 75% of the interval, I ran something that was not the highest priority. I'm just going to go down the list. That's going for each CPU. After the CPU list, let me just find a code 2 here. We then have a summary for each process that ran. I'm going to look for a code 2. So here is a code 2 that ran during those 15 seconds. So this summary says the PID was 12347. It got 479 time slices. The total run in milliseconds was 9.154 seconds. So I was getting an average of 19 milliseconds per slice versus the 100 millisecond slice size that we would have liked to have gotten. And again, I was locally queued 480 times. The total milliseconds I was queued locally was 5.5 seconds. The average residency time in the CPU was 11.8 seconds. So that should approximately add up to 15 seconds, but it's looking a little off. I never got queued globally, and I was never on a global queue, so I had strong affinity. And I never went to sleep during that interval. I had 480 context switches for that process. 295 of them were short preemption. And that's what we saw when we looked at the average residency. It was less than 100 up here. It was less than 100 milliseconds. Okay, so I was preempted short 295 times, and then preemption long 185. No sleeps, that's what Janet had mentioned. And then what I was saying was the yield, or SGI naps. And none of those occurred either. And must run says I'm locked down into a CPU. By the way, the next line is actually showing me a kernel thread rather than a user thread. And this particular kernel thread is some sort of netproc process, but it's going to have a KID with a number after it. Now that was the summary report. And again, IRIX view will give you the exact same information. The next one is with 3 queues.
3 times as much information?
More. We had 2,000 context switches in that interval, so there's going to be a record of every one of them. Unless PAR starts losing events, like we saw the other day at a PAR trace where a bunch of event numbers were missing. We couldn't keep up with the CPUs because they were always in the kernel doing system calls. It's even taking longer. Of course, the workload could be interfering too.
Workload? What workload? It's only 25.
Wait for this to finish. Okay, I got my prompt back. Now when I look at CT file, it's going to tell me about each one of those context switches. In fact, this should be interesting. It took a while for it to run, and it's all CPU work. There's no indication of I/O. There's no indication of anything else going on. It was pure CPU bound. So now with a 3 queues option, the PAR is now tracking every single context switch. Now the verbosity of this trace is going to change depending upon how old you are with PAR. But we've got the time since I started PAR, the CPU that I'm looking at, and then the program name. And this is the thread ID, since this is a kernel PCI interrupt handler daemon. And it says that it was on CPU 5 and it had a real-time priority of 210. Okay. Right after that, though, we got a context switch, and right here we see code 2 came into the system, and it was put on CPU 5, and it had a run queue priority of -2. Now the -2 says that it was running as timeshare versus real-time. So the interrupt handler was scheduled as a real-time process, but my interactive work is running as timeshare, and that's what the -2 says. And in fact, we then see code 2 being preempted or kicked out. This is a switch out of code 2. Then we see the CPU idle there for a second, and then on the run queue for CPU 5, we see this new thing come in. And that was this particular PCI interrupt handler. So if you look at the ID and everything, 42949673334. And then we actually see it switched in. And actually right after it, we see it switched out. Now this is an interesting one here, because we switched out and that daemon hit a lock. The lock address is here, but I don't care about the address. The semaphore we hit was THD_ISYNC. Now if casing name D were off, we would not see the lock name, we would see the lock address only. So casing name D says, I hit that lock and therefore got switched out. A little bit later, I see the real-time monitor daemon getting switched out on a kernel thread wait. It was waiting on the kernel doing some I/O, probably BD flush. So for every CPU, we can see what is on that CPU's run queue. So here's CPU 3 and CPU 5 showing the two PIDs for what's on those particular CPUs. I'm just looking to see what other kind of locks we're hitting, time in, timers. Okay. Now here is another shareware tool that is actually the no-ship tool. It's in that no-ship SW perf. We talked about top func. There's also a top wait. With top wait, I can actually see the locks that I'm context switching on. So we're still looking at this context switching. I have 138 processes, 16% of them or 23 are being preempted, none yield, and 85% of them are waiting. There's none stopped and there's none that are unknown. So I've got 5,421 context switches that just occurred. 42% of them are preempted, 57% of them are on waiting, no yields. And then here's the real-time monitor event saying how many events have I received and how many I've lost. And again, if I start losing events, that simply means the CPUs are busy and I can't keep up with the intensity of the events. So I don't care about the WCHAN field, but having casing name D turned on tells me that these are the locks that's driving my context switching. In fact, we saw that in the trace as well. THD_ISync is at the top of the list. 18%, 19% of the context switches are from that particular lock. 483 per second. This describes what type of lock it is. It's a semaphore, an SB lock. There are different types of locks that are documented. So this is giving me the frequency information, but not how long I'm waiting on the lock. I can't see the lock timings. If I want to see lock timings, there is the ability in that casing name D area to turn on lock statistics, but you don't, that's for developers, you don't run that normally. Unlike a Cray where we got lock statistics from SAR all the time, so we can see the lock name, number of times the lock was hit, and what was the average time spent on the lock. So there is a lock stat command that can give me the time statistics for these locks, but this is frequency statistics. And again, I'd go off to my web page and look up THD_ISync, so let me just do that. THD_ISync is part of the X-thread setup. Then I'd have to know a little bit more in the kernel what X-thread setups are all about, but I could go into the kernel and look that thing up. And that happened to be a init NSEMA. It was a semaphore type of lock rather than a mutex lock or some of the other types of locks. So I want to go back to the workbook, and what we were just talking about was how these processes context switch, and if they voluntarily yield, or if they get switched out due to priorities. And we're basically trapping with *R all of our context switches. Now this is the biggest thing that customers are experiencing. They completely rewrote the CPU scheduler from 6.2 to 6.4. Of course 6.4 shouldn't be running out there anymore. It was an intermediate release for Origins. But 6.5 is essentially the same scheduler. In the process of rewriting a scheduler, all kinds of behaviors change. And that's what the customers are seeing. So they rewrote it. First of all, they said poor scaling past 24 CPUs. This was where they created a run queue for every CPU. That way I don't lock out the entire run queue. If I run a 512 CPU origin, I don't want to lock the run queue and have 400 CPUs looking for work, waiting for that lock to get released. They said the schedule had high overhead, limited real-time, poor parallel scheduling. I'm not agreeing that these actually occurred, but poor batch processing, narrow priority range. It was not POSIX compliant. There is particular, and Unicos is not POSIX compliant either. So some of the differences between 6.2 and 6.5, first of all, there are no longer what are called degrading priorities. Degrading priorities was in the real-time, or I'm sorry, in the timeshare band, and you'd actually see the priority shift depending upon what this priority was. Those are hard to predict, so they got rid of it. And we used to play that game in Unicos with the share scheduler too, throw a simulation in a share simulator and then see what our priority is going to be and try to predict what the scheduler is going to do. So a lot of customers do want to throw a scenario at the system and say, is it going to run the work that I want? And in my example, is it going to get code 2 through the system with higher priority than anything else? Also, they got rid of the deadline scheduler. So that was something older. And that is replaced with something called React, or the real-time package, also referred to as the frame scheduler. So that's more for the real-time market. This is the one that I get hit on all the time from customers. There's no more P-sets. P-sets were replaced with the miser CPU set command, but it doesn't behave identical. It doesn't behave exactly the same. Now, Mountain View developers chose to change the name of it. They said, well, P-sets are not NUMO aware, and P-sets actually came from Sun. So they had to pick a different name. Then miser got bad press out there, so to speak, because not enough sites were running miser. It was brand new and it was unstable. And also people don't like a reservation system concept. They think they can just walk into the restaurant and get a table. So in the process, miser got kind of a bad name to it, and they renamed this command CPU set. And you will find a link between CPU set and miser CPU set. It's the same command. But it's not using the miser daemon. The biggest thing, however, is that in 6.2, gangs were favored. The more threads I had, the more CPUs I got. In 6.5, the developer said, I do not want interactive processes to get interfered with by these gangs. So they now distribute my CPU time by process group. Now, standard Unix and older IRIX distributed by process. So if I fired off 100 processes and you fired off one, I would get 100 times more than you would. The schedule would try to make sure every process or every thread gets an equal slice. So if I fire off 100 processes, I can dominate the CPUs and drown you out. I can hold all those CPUs in the older IRIX. But now, I get penalized. And this is what's referred to as currency scheduling. The more I use it, the lower my priority drops. And it's distributed by process group. So when I fire off my multi-threaded application with OpenMP, all the children threads are in the same process group ID. Okay? So now if I fire off 100 processes and you fire off one, we still get equal. If it was a 100 CPU system, you'd get one and I'd get 100. But if it was a 2 CPU system, you'd get 1 CPU and I'd get 1 CPU. And my 100 processes would be fighting for that 1 CPU. Okay? So this is the biggest thing, and this is why code 2 took 2 weeks when it had 100 seconds worth of work. Because the scheduler would not let all these threads get connected as a gang and allow them to get their work done and talk to each other. As they did that, they would lose their priority. The more threads wide I go, the quicker I lose my priority. The more CPU time I consume in parallel, the quicker I lose my priority. I like to call this thing the equal share scheduler. Now the fair share scheduler distributed by user ID, this is distributing by process group ID. That's the big difference. And I'm going to come back to some of that. So, in 6.2, 0 was my best priority and 255 was my worst. But that is not POSIX compliant. They completely flipped it around in 6.5. 6.5, 255 is now my best priority and 0 is my worst. Go ahead, question.
If you run someone that's waitlist, it shows it's 255.
We'll have to talk about that, but I'm surprised to see it as 255.
Let me verify that.
Yeah, go ahead and try it. And we'll come back to that. There's one other thing we have to talk about, and that's classes. So this is the older way, this is the newer way. Now in the older way, my system daemons were from 0 to 29. If I still code them, have them coded, they will automatically, those binaries will map to 155 to 255. But in actuality, the system utilities can go, system daemons can go anywhere from 129 to 255. Real time used to be 30 to 39, so there are only 9 steps, 10 steps in the ladder. And those will still map over to 129 to 156. But now, the real-time market is 1 or 0 to 255. So instead of 9 steps, I've got 255 steps that I can stack or prioritize my processes in. And with real-time, I can go what's called first in, first out, which means I get the CPU until I yield it, or I can go round robin and let the clock interrupt allow somebody else to take my CPU from me. Timeshare was 40 to 128. Now it's 1 to 40. Much smaller priority range. It basically maps with the nice value. Then we also used to have the batch with priorities 128 to 255. Those are gone, and everything there is basically weightless or miser. Now, I'll come back to some of this stuff, but the next thing we have to realize is when I go looking for work, I do it by classes first. Every class is different in terms of how I find work. So when I go idle, I look for real-time first. Any real-time of any priority will always run before any other program. So I will always look for real-time first. I will look for the one with the highest priority number, and if 2 are at the same priority, I will pick the one with the larger CPU wait time. So I could have a real-time priority 0 that would run before anything else on the system. It's pure priority driven. None of the others, priority has no meaning. The second class that I have here is called batch critical. If you've ever popped up top, we're going to see it as a BC showing up in top. So batch critical is miser. Now miser has no priority scheme at all, and nice has no meaning at all. It is purely first in, best fit. 15 years ago when I started teaching NQS or batch interfaces even on COAS, in those days we called it job packing. And we draw out a timeline and a memory size and figure out how I can pack my jobs into the space to get a benchmark done as quick as possible. The spawning order and stuff like that. And that's the best way to describe miser. It's a first in, best fit. Okay, so if I take my reservation schedule concept, maybe this is 8 hours during the day. And then this is memory over here. And for example, I may have one program that runs real small, got submitted first into the queue, so it got packed there. Then somebody else comes along and submits to miser and says, I need more memory, and it can't fit in here because it's too big. and it packs in here. So this is the memory size, and this is the CPU time. Now if somebody were to submit something that was small, instead of packing in here, even though I submitted after this person, it would say, wait a second, that will fit, and I will pack it in here. So I might have done this one first, this one second, and this one third, but it could not pack in here, but the one that was submitted after it could. So that's what I mean by first in, best fit. If somebody takes the whole reservation, and now I try to submit that code 3, and there's a code 3 here already, and I try to submit to it, the whole reservation book may be full, and I will be told, retry later. My segment, my reservation book is full. So priority right now has no meaning in Miser. In the future, they plan on adding a priority concept to it, but there's no priority concept right now. It's basically a first in, best fit. Now there's something new that happened in 6.5.4 and beyond. 6.5.4 got into what was called repack. And with the repack concept, it is actually going to shuffle things around and periodically try to repack. Maybe this job finished early. So it finished in this time, and somebody else, instead of submitting here, actually was able to take advantage of that quanta and run their fourth job in there. So a repack is basically taking the reservation book and shuffling everything. Ironically, prior to 6.5.4, the reservation manager had no eraser for the reservation book. If I reserved this memory space and then killed my Miser work, the reservation remained. Okay? It had no eraser, it had no ability to shuffle. So that's what repack is all about. Repack says periodically reshuffle these reservations. Okay. So right now, nice has no meaning, priorities have no meaning, it's first in, best fit. When you submit to Miser, it tells you, here's when you're going to run, and you are guaranteed the CPU and the memory while you are running, while you are batch critical.
It was my mistake, waitlist, that was on 6.2, it shows 254. Under 6.5, it shows a W.
Okay.
That's all it gives for priority.
Yeah. That's what I expected, actually. So I think he was thinking that 255 was for the older 6.2. It just shows a W because there's no priority scheme anymore. And that's what I'm trying to say right now, is that priority only matters in the real time. Everything else is not a priority-driven scheduler. The only time I look at the priority number is if I have real-time processes. So batch critical will have no priority number there. It will show a BC. Waitlist is showing a W. Now the timeshare ban, first of all, there are two ways of running timeshare. One is standard IRIX, which is called the currency scheduler. And that distributes by process group ID. The other possibility is the fair share scheduler, or share 2. But SGI no longer has a support contract with the vendor for share 2. I do have customers, even 2 weeks ago, one of my customers that I worked with was running the share 2 scheduler. Share 2 distributes by user ID, where standard IRIX distributes by process group ID. So if I load share 2, the way the timeshare ban works is different than without share 2. But it is still not priority driven. It is based upon earnings. So every time I use the CPUs, I spend money, and every time I stop using the CPUs, I accrue money. It's very much like the fair share scheduler, but fair share scheduler usually tries to equalize across hours or days, whereas this currency scheduler is equalizing across a second. So every second I'm doing my normalization of these numbers. Anyways, we'll come back to that. The timeshare band is where everybody is running by default. When I log in, I'm in the timeshare band. That's the default. So all the interactive users run in timeshare. And remember that currency scheduler is going to penalize multi-threaded applications. The next class is called Opportunistic Batch. Now this will probably go away because of repack. Think of Opportunistic Batch as the bar before you get your table. So I call the restaurant and they say, you can be here at 7. And I get there 10 minutes to 7, my table is still dirty, they'll put me in the bar. Okay. While I'm batch opportunistic, I can still run. The trouble is that everyone else keeps kicking me out, and the opportunistic ban causes severe system cache thrash effects. So all those variances in code 2 are going to get much worse when I'm running opportunistically. So what they want to do is get rid of opportunistic and go all batch critical and simply do the repack more often. Because what would happen before is maybe, just looking at this, maybe this job finished early. So now in the reservation book we had an open slot where something could run. This next job that was in the schedule would then try to run opportunistic with just a B there, but it would thrash like crazy. So once they did a repack, they simply packed everything in, and then we can run as batch critical. Again, real time will show up as RT with a priority number. Batch critical will show up as a BC. Timeshare will show up as TS. Opportunistic batch shows up as B. And then lastly is waitlist. Rather than go idle, we go waitlist, and that shows up as a W. So we'll always look for real time first. If there's nothing there, then we go batch critical. If there's nothing there, then we go timeshare. If there's nothing there, then we look for opportunistic. And if I still don't have work to do, I will look for waitlist. The lower you are on this list, the more you're going to thrash. Now it is possible, we'll get into this a little bit later, for me to skip the opportunistic ban and go straight to batch critical. And that's called static. And that's what I need to do with code 2 to get repeatable timings, is I need to get it running under miser with static mode. So just think of miser as that reservation book with a memory and a CPU time and also a number of CPUs. So you're declaring how many CPUs you want as well. So that's what this drawing is trying to show. When I go idle, I look for real time first, then I look for batch critical work, then I look for timeshare, then I look for opportunistic, then I go waitlist. And periodically there's a scheduler tick that causes me to kick out of the CPU and look for work. Every 10 milliseconds I'm going to get a scheduler interrupt. So, all timeshare processes get CPUs in proportion to their earnings based upon their nice value. Now this is the disadvantage. Remember I said earlier that degrading priorities were hard to predict? So what the developers did was hide the stuff so that you can't see it. So you could have 2 programs at the same priority, but you can't predict which one's going to run next because you can't see their earnings numbers, the currency account numbers, because they're constantly changing. It's not like fair share where you can pop up an L node and see what my usage was and what my entitlement is and stuff. Okay? So all timeshare processes are based upon nice. Nice simply changes the priority number that's printed out, but that doesn't, we could have something with a lower nice value that actually ran before something with a higher nice value. Second line here, just talking about real-time processes. We're guaranteed the highest priority process until it yields with the system call, blocks on the system call lock, or exceeds its time slice. If there's more than one high priority process, the priority process in a job class waiting the longest is granted a CPU. And again, a running process is preempted when a higher priority process becomes runnable. So in the interactive ban, this earnings-based scheduler you could also refer to as a space sharing policy. It's appropriate for interactive timeshare environments, but it's bad for parallel. Okay? Because in the parallel environment, I'm consuming CPU's time faster because they're all in parallel, and I'm going to lose my interactive priority that much quicker. So Mountain View basically said multi-threaded applications do not belong in the timeshare ban. They will get penalized there. This is one other comment. Default allocation places a real-time process on a CPU with no other real-time. Remember yesterday I said I put 2 threads per node board? The real-times go 1 per node board. So if I have a 16 CPU system with 8 real-time daemons, that means there's going to be 8 real-time daemons each on one of the nodes. And in that scenario, I might actually do a DSM PPM and set it to 1 so that the application gets one CPU and the real-time gets the other CPU. And then the other CPU that's running real-time may be not used and may be idle a lot. But at least the real-time can get it as soon as it needs it. So this timeshare space sharing policy is designed to multi-process the timeshare applications from preventing them from dominating compared to earlier versions of IRIX. In other words, we do not want gangs to gang up on our interactive user. And that's why they did it. And that's why Code 2 has barrier synchronization problems. And the purpose of the space scheduler space sharing is to maximize the CPU throughput. I don't want to have context switching and have things constantly warming cache with data that should have been kept in there private or exclusive. So anyways, jobs that require multiple CPUs run proportionally less frequently. Multi-threaded applications are going to consume CPUs faster and lose their priority that much more quickly. In the interactive band, NICE affects the rate at which the earnings are accumulated. It does not affect the priority as such. Changing the priority results in changing the NICE. Basically, NICE and priority are mirror imaged of each other for the timeshare band. And again, currency is spread across all processes in a process group. So every process group ID is going to show that. Also, IRIX tries to keep a process on the same processor as long as possible. This is significantly improved in 6.5.8 and beyond. Prior to 6.5.8, it wasn't very good. You had a lot of thrashing going on. And when we looked at the Perfex reports yesterday, it popped up a couple of bottleneck curves. One of them were very clean, and then I showed the latest one. It had a wider variance where some were staying locked down, but then the ones that lost affinity were much worse. So we want to keep the process on the processor as long as possible. It reduces the need not to flush cache. You should cross that off. That should be to warm the cache. I come into the CPU, I load the secondary cache with my data. I don't want somebody else to come in, grab my CPU, and then warm it with their data, because then when I come back in, I'd have to warm again. Whereas a flush is the false cache sharing problem. I write into cache, and now I've got to flush it to disk. Or flush it to memory, I mean. So the whole purpose of cache affinity is to reduce the need of warming the cache every time I bring a new process in it. Also, we want to keep it on the local board to prevent having to move the memory around. We want the process close to the memory it's using. Now, there was a dispatch group. There's a flag called memory affin sched. I see no reason to turn it off. I've never seen anyone turn it off. On that particular system parameter, I simply tell people, if there's a red button in the cockpit of your jet, are you going to push it? Depends upon your situation. But I've never seen anybody actually set that to 0. And we also talked about slice size to keep me on the CPU longer. And again, slice size was 10, which means 10 times 10 milliseconds, or 100 milliseconds total. And that was the third clock tick up opportunity up there. And if I'm in the real-time market, I can use the system call sched-ctl to control my affinity. Now, this is just real quick. Kernel has threads. The threads are typically real-time, and they have a priority scheme. The real-time man page will actually document the priority scheme of some of these daemons. So sched, vhan, bdflush, acfail, rtnetd may have certain priorities. Now, in the newer systems, sched, vhan, and bdflush are kernel threads, but they still have a priority scheme. And systune, you can change those priority schemes. So all processes are assigned priority. It ranges from 0 to 255. Higher the value, the better the priority. Timeshare only go from 1 to 40. Batch are a 0 priority or weightless. Real time can go from 1 to 255, and real time can be either first in, first out, or round robin. Talking about changing the priority of the process, we have NPRI, we have NICE, and we have RENICE. So in the workbook, they did NICE. NICE changes the priority of timeshare only. NICE has no meaning in real time, it has no meaning in miser. So in this example, they fired off Atlantis, then they fired off Atlantis again, but they did a NICE 10, which dropped the NICE down, making it lower priority. So we can see the first one started off at a 20-20. When I did a -10, they then went to 10 and 30, and we should check on the fields for that. So PS.
Oh, I just bombed you.
That's okay.
Skipped out a whole nother batch.
So I was going to do a PS-L. The first one was the priority, the second one was the NICE. So when I did a NICE -10, my 20 went to 30, and the other 20, which was the priority, went to 10. By the way, there is a difference between Unicos and IRIX. In Unicos, when we did the ampersand sign, we dropped down 4 automatically. We also had our user database support the ability to drop our NICE when we logged in interactive, which IRIX doesn't do either. And that was rather nice, so that I could have batch running at normal NICE of 20, but every time somebody logged in, they'd come in at 24, and if they used the ampersand sign, that thing would fire off at 28. That way your background program doesn't maroon you and maroon your interactive environment. But IRIX doesn't do that. The other command is NPRI, so I can set